Okay, so welcome back to the session. Here comes our next speaker, Professor Tadahisa Funaki. And the title of his talk is Interface and its Fluctuation in Interacting Particle Systems. So let's enjoy. Next is
Yeah, thank you very much for kind introduction. So this is the motivation of my talk, and roughly I summarize my result. So the motivation comes from the physics, and it is called a dynamic phase transition, or a dynamic phase separation, or dynamic phase transition. And as I said, it is coming from the physics literature, especially statistical physics. And what we discuss is we consider the microscopic interacting particles. That is a very simple one. So we consider random walks on the lattice, but there are many particles on the, and also the lattice size is very large. Then we will show that there is an autonomous separation into dense and sparse phases. So there are two phases that is related to this phase transition. So the particle systems autonomously separate into two phases. Then that means there is a density threshold, which we will call rho star. And the region that the particle density is bigger than rho star immediately falls into the dense phase. Actually, this is just the image. So we have two phases. So this is the dense. There are a lot of particles. And outside, it is sparse. So autonomously, if at the initial time, the density is roughly bigger than rho star in this region, then it falls down to the dense phase. And if outside at the initial time, the density is smaller than this threshold rho star, then immediately it falls down into the sparse phase. So this is a microscopic picture. Then we move to the macroscopic picture. Then we can observe a sharp interface which separates dense phase and sparse phase. Then we will show that this interface evolves under the anisotropic curvature flow. This is the law of large number in the probability theory. So starting from this, we arrive at some deterministic evolution. And especially, this is a bit technical, but the model we consider is so-called the non-gradient model. And for the non-gradient model, okay, Baladan considered this kind of model already 30 years ago. Then there was no progress afterward. However, recently, Chenlin Gu and also some of my colleagues made a great advance. And his argument is recently upgraded by extending recent method in quantitative homogenization theory, which I want to explain later. I have some simulation, but maybe the video doesn't work on this PC. Therefore, I just skip. So we have this picture. Then also we discuss the fluctuation of the interface. Fluctuation of the interface. This means you look at, so this is a law of large number. Therefore, the limit is deterministic, but you look around the interface, and then, of course, there is a small fluctuation. But in this scaling, we don't observe. So we introduce a different scaling. Then we can observe some fluctuation. Then, actually, we can derive the stochastic PDs. And also, this is heuristic. So this part is already done. But I expect some nonlinears. So this is a Gaussian limit. So we get some Gaussian fluctuation. Originally, the interface fluctuates very little. However, we introduce another scaling that is a stretching to the normal direction to the interface, and we can observe some fluctuation. Then it is described. So then we have some random structure. Then we have a stochastic PD. But this is a Gaussian object. However, we can expect, so this is not done yet, but we can expect under certain scaling, some nonlinear stochastic PDs can be, maybe we can derive, including especially the KPZ equation that is recently attract a lot of attention. So this is the outline of my talk. So first section, I explained what kind of dynamics. So this is a random walk on the lattice with Glauber means some creation and annihilation of the particles and some certain scaling from microscopic to macroscopic. Then the first part, so this is the second section, but the first part is the hydrodynamic limit. So this is the law of large number. And then we will derive the interface motion. Then the last section, I want to discuss the fluctuation of the interface. The important role will be played by the so-called Boltzmann-Gibbs principle. So this is a picture of my collaborators and Chenlin Gu actually sitting over there. So with him, and also he's a Yale Mathematical Science Center, and also Wang, I don't know, he's sitting maybe here. So he's still undergraduate student at the chosen college. So I'm very happy to work with them. And so they are very clever, I think. And they proved they applied the method of the recent progress in the quantitative homogenization theory, and we can apply now to the hydrodynamic limit, which is, in a sense, an infinite dimensional problem. So homogenization is a finite dimensional problem. But, this hydrodynamic limit is, in a sense, an infinite dimensional problem. Yeah, in a sense. And then I worked with Hyunjoon Park. He's originally Korean, but he's now in Tokyo. So he works on the PD. Therefore, we worked on the singular limit for a nonlinear Allen-Khan equation and derived an isotropic curvature flow. And then now recently, I'm working with Claudio Landim in IMPA in Rio, and also Sunder Sethuraman in the University of Arizona for the fluctuation of the interface and derivation of the stochastic PDs. So I'm very happy to work, especially the young colleagues in the Tsinghua University. So, okay, so the Glauber-Kawasaki dynamics and its scaling. So Glauber, he is a Nobel Prize winner, and also Kawasaki, he is a Japanese, and he also got a Boltzmann medal. So Glauber considered in this paper already a long time ago, I think 1963, time-dependent statistics of the Ising model. So he introduced the dynamics corresponding to the Ising model. But in his model, there is no conservation law. But Kawasaki considered the corresponding dynamics, which has a conservation law. That is sometimes called the Kawasaki dynamics. So based on these models, which we want to consider is the following. So in the last page, it shows Glauber-Kawasaki dynamics. This is a combination of the two effects. It's originally a dynamical Ising model. But the Ising model takes a value of the plus minus 1, but maybe minus 1 is a vacant site, and 1 is an occupied site. So in our case, we write instead of plus minus 1, 0 and 1. And so 0 means that there is no particle, and maybe the circle means that there is a particle. The configuration eta x equal 1 at the position x. And we can interpret in that way. So Glauber-Kawasaki dynamics is nothing but interacting random walks with the hardcore exclusion rule. Exclusion rule means only one particle, at most one particle can occupy each site, not two particles. So that is a hardcore exclusion rule. And this is the Kawasaki part because particle numbers are conserved. The total particle number is conserved. So Kawasaki part has a conservation law. On the other hand, the Glauber part in this picture describe the creation and annihilation of the particle. So by Glauber part, maybe 1 becomes 0 at some rate, and 0, so here is no particle. Then a particle can create it, then the configuration becomes 1. So that is described by the Glauber part. So we consider the mix of the two effects. Okay, so for simplicity, we consider on the lattice discrete. So this is a square lattice, discrete square lattice. The size of the side length of this lattice is n. So eventually n goes to infinity. So this is a microscopic system, and they interact with each other. Okay, so this is then, actually the dynamics is described by the jump rates. Jump rates. So Cxy eta. So eta is the configurations. Sorry, maybe I should explain. Eta is so we call eta the configuration. So eta x is, so this point eta x is called 0 or 1. The collection of the eta x is just called the eta, and the space of this configuration space that is denoted by xn. Then jump rate is given for, or the maybe exchange rate. So Cxy eta, so depending on the configuration and the position x and y, which is actually the neighboring sites. So we just exchange eta x and the value of the eta x and eta y. Eta x is 0 or 1, eta y is 0 or 1. If both are 1, then nothing happens. Both 0, nothing happens. But in case that eta x is 1, eta y equals 0, that means a particle jumps from x to y. And if eta y equals 1, eta x equals 0, the particle jumps from y to x. So this is considered as the jump rates, or maybe we can say it's exchange rates. And we assume the detailed balance conditions. So actually, eta x, Cxy eta doesn't depend eta x and eta y. So this simplify actually. And under this condition, the Kawasaki part, the random walk part, as the independent Bernoulli measures new eta, so but new rho, sorry, new rho is parameterized. So this is the density, macroscopic density. So rho runs from 0 to 1. And the Bernoulli means it's just a product measure. So product measure becomes the invariant measure, or the reversible measure, or maybe equilibrium measure in the physics sense. And especially the current. So this is the rate, one particle jump from x to y, and also the minus y to x. This is a rate. It's not of the gradient form. This is non-gradient. So if this is some gradient form, then it helps very much. But in general, we don't have such property. That makes this problem difficult, in fact. For the Glauber part, we have flip rates. That is Cx eta. That is flip means from 0 to 1, or 1 to 0. So eta x goes to 1 minus eta x. So this rate is given by Cx eta. Sorry, maybe this is x instead of 0. Sorry, maybe this is also x. So anyway, in case that eta x equals 0, then there is no particle. Then after this flip, a particle is created. Therefore, this describes the creation rate of a particle at x. And on the other hand, if eta x equals 1, there is a particle at x. Therefore, this describes the annihilation rate of the particle. And yeah, actually, we actually tune this rate. This is set to favor two levels of the particle densities, rho plus. So we want to discuss the effect of the phase separation. Therefore, we want to make two phases. That is a dense phase, that is a particle density average, is given by rho plus, and the particle density average rho minus. Rho minus is smaller than rho plus. So we want to tune this rate in such a way that the particle system actually likes to have one of these phases. So we have to choose anyway. I don't write very carefully, but we want to make sparse and dense phases to realize it. Then the particle actually fall down, one of them, by tuning in a proper way under this flip rates. And also, yeah, balance conditions. So the two phases are actually balanced. That means the same degree of the stability they have. I will explain maybe later. And we assume some basic assumption. It is finite range. So this depends on the configuration. That means there is an interaction through this jump rates. And also there is an interaction through this flip rates. But it is finite range. Finite range means it depends on the ether, however, not so far. So anyway, we assume such finite range property, and also the mechanism is translation invariant. Then scaling. Then we come to the scaling from micro. So in this way, we gave a jump rate and also flip rate. Then we have a microscopic random walk systems. Actually, very simple anyway. But we have an exclusion rule. Then, so the configuration changes in time. Therefore, we denote its eta t because we consider the time evolution, and it depends on the size of this torus, discrete torus. Then, actually, we consider the Kawasaki part with the n square. So depending on the size of the this lattice, we put the n square. So we speed up. We speed up by n square. This is actually the diffusive scaling. So from random walk, you can derive the maybe Brownian motion like that. The space size is n, then we put the n square for time. This is a diffusive scale, usual diffusive scaling. And on the other hand, for the flip rates, we put the k. K also depends on n, but it should be much slower compared to n square. So, but it should also diverge with n. So we in a sense introduce a time change. So Kawasaki part moves like a diffusive scaling. It should go to something like a Brownian motion for if you consider one particle. Then this creation and annihilation part also speeded up, but it's much slower than n squared. So later, we will assume kn is like log n. So it goes to infinity. However, it's very slow compared to the diffusive scaling. So this is the time change part, scaling in time. Then, we have a microscopic random walks, interacting random walks. Then, also that we scale the space. X is the microscopic position, and it is huge. X is huge in a sense, but we divide by n, so x over n. So microscopic space is huge. However, we just shrink down its size by dividing by n. Then at the macroscopic scaling, it should converge to the unit torus. So Tn denotes the unit torus, but a continuous torus. So we put this is considered as a mass. So microscopically, the mass is 0 or 1. If there is no particle, the mass is 1. Then we put the mass at just changing the space by shrinking down this size by dividing by n. Then we also, so this is the scaling in space. Then we also scale down the mass by dividing the n to the power d. So n minus d. So we divide by n to the power d. So we change the mass of each particle from 1 to n to the minus d. So so in the total mass should be order 1 in this scaling. So we consider this scaling. So starting from microscopic system, we introduce the time change and also the space change and also the mass change. So we sometimes call this is macroscopic empirical mass distribution or the macroscopic maybe density field. The microscopic space is denoted by X, so that we denote by V the macroscopic space variable. So the goal, what we want to study is the limit of this macroscopic density field as n goes to infinity. This is what we want to study. Then this is a quantitative. That is called the hydrodynamic limit because to derive the limit equation, actually the essential role is played by the so-called local ergodicity, local averaging effect. And it is related so that to derive the hydrodynamic equation, for example, from the Boltzmann equation or the maybe Hamilton system, so maybe from the Boltzmann, maybe you go pass by the Maxwell distribution. But the Maxwell distribution is not unique. And the structure is very similar to our case. Of course, the dynamics is very different. However, the structure behind is very similar. So in probability theory, it is called the hydrodynamic limit, although it is not really hydrodynamic equation. Okay. So, and then in our situation, we can derive the interface motion which separate the sparse and dense phases. And then I want to emphasize that the particles autonomously make phase separation into sparse or dense phases at microscopic level. There is some threshold rho star, and then between the sparse and dense densities. And if as I said at the beginning, if the density is bigger than this one, then it immediately falls down to the rho plus phase. And if it is smaller than rho star, then it immediately falls down to the rho minus phases. Then the phase separation curve, in a sense, we can observe. Then it evolves, in fact, at the macroscopic level, an isotropic curvature flow. This is roughly what we can prove. And we need some assumptions, entropy condition. So initial distribution, we need some entropy condition compared with some local equilibrium state, and also some technical condition to apply some PD techniques. But anyway, roughly, and also, as I said, K is not so it goes to infinity, however, not so fast, like some constant which should be small times log n. So it should go to infinity, but rather slowly. Then we can prove that this is a macroscopic particle density compared with anisotropic curvature flow. Maybe in the next page, I will explain what this xi means. And multiplying the test function phi, and then we integrate, and then for every epsilon positive and t between, so capital T is also, I will explain in the next page. And gamma T is actually this is some interface which separates two phases. And then this is defined from the microscopic system, and some scaling is very close to this one. But through we look through the test function, and this is in probability sense. So, but we can estimate the convergence rate of this. So kappa is a positive. So, we can find some positive number kappa, and this converges in this rate. And that is called the quantitative hydrodynamic limit. And I think this is never, for the non-gradient case, this was not known before. Gradient case, it was known, but non-gradient case is very difficult, actually. So this is a very good point, and I'm very happy to work with young colleague at Tsinghua. this is essentially their contribution, not my contribution. Okay, so maybe I should explain what is a xi. Xi, so anyway, first we determine gamma t, the time evolution of the gamma t. The evolution of the gamma t is governed by some non-linear. So this is actually v is the normal velocity of the gamma t. So we have a gamma t from the rho minus side to rho plus side. Then the normal velocity of the gamma t is given by this formula. So n is the normal direction, unit normal vector to gamma t, and so we can. So this is some macroscopic effective constant, which is a matrix, but this is certainly we have a formula for this one is determined from the Kawasaki-Glauber weights cxy and cx. We can write down explicitly what is this one. So anyway, this is we can write down this as a nonlinear PD, in fact. And as long as gamma t is smooth, this nonlinear PD is well posed. That I don't write very carefully. Then t is the time such that has this one as a smooth solution. So we don't consider after some singularity happens. Maybe gamma t after some time maybe exhibits some singularity. However, our result is up to the time that there is no such situation. And xi is just a step function. So inside gamma t, we put a plus, rho plus. The outside of the gamma t, we put a rho minus. So this is the average density in a sense. Then xi is a just step function. The inside, microscopically, we reach dense phase, and the outside of the gamma t, we reach this sparse phase. Then macroscopically, gamma t evolves with this along with this equation. Okay, so we actually assume the balance condition means that this phase, so I don't formulate very precisely, but this phase and this phi phase have the same degree of the strength. However, we can also consider the unbalanced case. Then I have a paper, slightly different model with these people. And we can derive so-called the Huygens principle in the unbalanced case. So, for example, rho plus has a much more strong strength. Then the phase rho plus actually expand as the time passes. Then the dynamics is different. Also, the scaling is also different. And then the stronger phase, for example, rho plus, this region expand as the time passes. That is a Huygens principle. But scaling should be different. And in this case, we have a growing interface. Then it's very similar to the picture of the KPZ equation. So I have some heuristic argument to derive the KPZ equation, but still far away to reach, to give a rigorous proof. But anyway, a balanced case is also interesting. Then, okay, so the proof. How about the proof? So the proof of this theorem 1 means we have a derivation of this one. So we want to give just a sketch of the proof of this theorem 1. So in fact, the proof is separated in two parts. First one is we approximate this one by the solution of the nonlinear PD. Then for the nonlinear PD, we prove the solution converges to this one. So we separate this one into two steps. The first one is, in fact, we can prove this one. This is defined through the microscopic random walks under the scaling. Then in the probabilistic part, we call the first part, we prove this is close to the solution of the nonlinear PD, which is a nonlinear Allen-Kern equation. Nonlinear means This is nonlinear. However, the diffusion term is also nonlinear. We can approximate the solution, and still this rho PB is the solution of this nonlinear PD, but still it contains a K. K depends on N. Therefore, this one is also changing in N. So the first step, we prove this one is close to this one. So I have an experience already almost 30 years ago. When the K equals 0, this one, so there is no Glauber part, then this converges to the solution of this nonlinear PD. I worked with H.T. Yao and also Uchiyama almost 30 years ago. Therefore, I had already experience for this equation. And Dij is given by so-called the Green-Kubo formula. And, but we now have some diverging this part also. This is sometimes called the reaction term, and this is the diffusion term. And or it is known as a Alenkern equation. But usually Alenkern equation is a Laplacian, the linear Laplacian here. But in our case, we have a very rather complicated nonlinear term, the diffusion term. And the diffusion term is determined from the Kawasaki part, Kawasaki jump rate, and this one is determined from the Glauber part. So in the next page, I will formulate this one more precisely. And then once this part is done, in the second PD part, we may just, so this K still move. Therefore, we may, so this is approximated by this one. Then to know the limit of this one, so we may just study what is the limit of the solution of this equation when K goes to infinity. So this is just purely a PD problem. So in the second PD part, we studied what is the limit of this equation. And then combining to result, we get the main theorem. So maybe I can explain maybe quite roughly. So there is a formula for the diffusion coefficient, which is called the Green-Kubo formula. This is called in physics Green-Kubo formula, but formulated in the variational formula, especially due to Valadan. And then it is also called the Einstein relation. And then there is some variational formula to determine this part. And this one is defined through the microscopic system. So this is the Kawasaki jump rate. And we need some collection term, F. So this is a variational formula, but so this is simply not just a jump rate, but we have some extra factor F, which we call. And F is actually related to the second order approximation of the local equivalence. Then maybe in the next page or later, I will come back to this function F. Or we can consider F as a corrector in the homogenization theory. So it is in fact related to the homogenization theory. And if our model is a gradient, that is current has some gradient form, then we don't need F. Always F should be 0. Therefore, we don't need this complicated formula. However, the diffusion matrix is defined in this way through the rather complicated variational formula, and we need to consider additional function F. F is, in a sense, we make n the size of the torus goes to infinity. Therefore, F is in a sense defined on the whole space, whole lattice, because we should consider in the limit. Okay, so maybe it's not very important to give this precise formula. Then F term, reaction term is the average, ensemble average, so-called the ensemble average of the creation rate minus annihilation rate. So this part is defined through the Glauber part. So ensemble average comes from the local ergodicity. In the discussion, we average our system. The ensemble means equilibrium state. In our case, it's very simple. It's just a Bernoulli product measure. Now, of course, maybe Gibbs measure case is more interesting. Canonical Gibbs measure case is more interesting. However, yeah, technically, it's much more difficult. So we simplified this as just a Bernoulli product Bernoulli measure. And this is anyway the Glauber part determines this macroscopically the effect of the reaction term. Then, for the probabilistic part, we approximate our macroscopic density field by the solution of this nonlinear PD in this sense, but with the convergence rate. And this is called quantitative hydrodynamics because we have a convergence rate. This is close to improbability. Improbability means for any epsilon positive, you have this estimate, and it is approximated by this one. And in the paper with Chenlin and Han, we have another paper we discuss just Kawasaki case, but the estimate obtained here is quite essential to prove this one. And maybe I didn't explain the relative entropy. So for initial value, we assume something for the relative entropy, but okay, so maybe it's not so important. So we have to assume some conditions stated above, especially for the initial distribution. Initial distribution of the particle system is close to the, in fact, the local equilibrium. That is our assumption. Okay, the outline of the proof of the theorem 2. And we consider the relative entropy of the real system compared with the local equilibrium state. Local equilibrium state is the Bernoulli measure, but the local equilibrium means this mean of the Bernoulli measure changes in space or also time. So space-time dependent Bernoulli measures, psi t is, so this part is the Bernoulli measure. However, we consider the non-gradient case, then we need the collection of this. So this is exponential, therefore it's a product. Sum becomes product. Therefore, we have a product Bernoulli measure determined from this part, but we need some collection. So f is exactly the same function as appeared in the variational formulas, the Green-Kubo formulas. Then, but this should be small, 1 over n. So this should be small, but we need a collection. So we actually compare with our real system. So this is determined from the particle system at the time t. Then we compare with this local equilibrium, but with the second correction term. Then we measure the difference by relative entropy. And we divide by n to the d. This is a volume. So we divide by the volume of the system. Then we just write it. So if this entropy per volume is small, goes to 0, actually we are done. If we can show that then applying the entropy inequality and large deviation estimate for psi t, just ft is closed. So this means ft, the real system is closed to this one. Then we can study the limit by means of this exact or the concrete measure. Then that is a large deviation estimate. Then we are done, in fact. Therefore, the main task is to prove this relative entropy per volume is small. It eventually goes to 0 as n goes to infinity. This is what actually we want to show. Then we use several techniques, Schauder estimate for the solution of the nonlinear PD and also local ergodicity, but is quite defined means the error estimate we need, and that is sometimes called the one block estimate. And also we consider the non-gradient case. Therefore, non-gradient part can be, the current can be replaced by some gradient function. That is a Boltzmann-Gibbs principle, also called, and also observation type estimate. And the most difficult is this part. And the Chenlin Gu and also Wang did, I think, a very good work. And they proved in this paper the convergence rate, this diffusion coefficient. So this is related to the diffusion coefficient. And the limit is a variation given by the variational formula. And they proved the convergence, they gave a convergence rate like this one, so like this one. And we can find the sequence of the function, this converges. So, but the range, so range of f goes to infinity in a sense. So this becomes large. Then this is uniformly in the density. We can find some convergence rate, and also some information on this Fn is given by in this way. So they proved by using the method of the quantitative homogenization theory, especially showing the modified Cacciopoli inequality and also weighted multi-scale Poincare inequality. For the so this is only for Kawasaki part. They proved this kind of statement, and this can be applied to our setting. And then we are done for this, also with the convergence rate. And I want to emphasize that originally Landim did to prove this kind of statement. He proved the characterization of the closed forms. This is like a Hodge decomposition, but in the infinite dimensional space. But however, but only by using his method, we can only show the qualitative, not quantitative. Convergence rate is not known. By using this method, we never get this convergence rate. However, by using this method, we even have a convergence rate. I want to say that this is a big step, I think. For 30 years, nobody could do that. Therefore, now, but we can have a very good estimate. Okay. Then the PD part. So PD part is just we show that this is, so in the probabilistic part, the macroscopic particle density is approximated by this one. Therefore, then in this part, we showed this converges to this step function. Also, generation and propagation. Okay, at the time 0, initial layer problem is solved, and also afterward, after the time up to capital T, we can prove this one. And the method is actually this is a parabolic PD. Therefore, we can apply the comparison theorem or the maximum principle, and we constructed the super and sub solution to prove this statement. Okay, so but I want to emphasize that the PDE is used only secondarily because in the statement of the theorem 1, the main theorem, no PDE appears. Therefore, this is in a sense a technique, I think. So we don't, yeah, of course we have to pass by nonlinear PD. This is very convenient. However, in the theorem 1, in the main theorem, only we are concerned with the particle system, and also a limit is given by this anisotropic curvature motion. Therefore, nonlinear PD, this plays no role in the statement, at least in the statement of the theorem 1. Therefore, but there is, I don't know, no other proof, but I would say that PD is only secondary. Okay, now I should move to the fluctuation of the interface. So so we derived this anisotropic curvature flow. And then we want to, so this is in probability theory, it's a law of large number. So it converges to the deterministic motion. Then we want to study its fluctuation. But fluctuation is, of course, very small, very small. Therefore, we need to introduce another scaling. That is the stretching by square root k. This is another scaling is needed. But at the moment, we consider only a simple case. We assume two things. One is Kawasaki part is simple. Simple means a jump rate is just one. So, so we just consider simple random walks, but with the exclusion rule. So there is an interaction, but we consider a very simple case. Then in the PD, actually the diffusion coefficient just constant at the diagonal matrix. Therefore, leading term becomes just a simple Laplacian. And then, moreover, we consider the stationary profile case. Stationary profile means we don't consider the time-dependent case. Just the profile depends only, and it is independent of t. Therefore, so that this PD becomes like this one. So no time derivative part. So at the moment, we consider a very simple case. That is the Kawasaki part is simple, and also profile therefore the interface is also very simple. So in this case, actually, this is we have some. So asymptotically, this means it is written. So there is a scaling parameter k here, but there is no k here. And instead of considering just b, so we stretch square root k, then eventually this space is order 1, but by this stretching, actually this becomes a whole line. Therefore, we consider U0, which is a solution of this equation, and with also the limit is rho plus and rho minus. So the profile of rho 0 is something like this. It is increasing from the low density part to the much dense part, sparse part to the dense part. Then, in this setting, just the interface is flat, and it doesn't depend on t, and something like this one. And we decompose the spatial coordinate v to the normal direction and also tangential direction. So this is the normal direction to the gamma, and this denotes the tangential direction to gamma. Then, yeah, we introduce the scaling only the first coordinate because the interface is flat, but the fluctuation is very small. But maybe we have to stretch it. Otherwise, we don't see any motion for the interface fluctuation. So then, in fact, the stretching. So we introduce the stretching in space, but not for the other part, and we consider the fluctuation around this limit. This is originally from the solution of the nonlinear PD3. Then we introduce a CLT scaling, that is n to the d over 2, because this goes to 0. Therefore, we have to multiply something goes to infinity. So this is the CLT scaling. And also, we have to introduce another scaling, which is also related to this scaling. Okay, so under the computation, the right scaling is a k to the minus 3/4. Then, actually, under this scaling, we have some noise, order 1 in the limit. So anyway, this scaling is taken in such a way that we get some fluctuation in the limit, non-trivial fluctuation in the limit. Then, yeah, this is just image. So originally, the interface is maybe original scaling, we don't see the fluctuation, very small. However, by stretching by square root k, we observe some fluctuation. And we want to we want to know what is the dynamics of this fluctuation. Then we consider time derivative in a sense. That is the Dinkin's formula or Ito's formula. We can compute, and then in the probability theory, we have a dt term, ds term, and also this is the ds term, and also this is a fluctuation term, which is called the martingale. Then for the martingale, okay, so there is some non-trivial term, which comes from the Glauber jump rate. So because the Kawasaki part is very simple, then it gives us just Laplacian. Kawasaki part gives us just Laplacian, but by the stretching, we have a large factor only the first this normal direction, k. This is due to the stretching. So this is essentially the Kawasaki part. And then we have some nonlinearity coming from the Glauber part. And then we consider it's a fluctuation, therefore you have to subtract its mean. That is, f was the mean of this one. Then under this scaling, we have this one, and also this is a fluctuation term, which we call the martingale. And starting this is usual, starting the quadratic variation, which is just maybe just the empty square and its expectation, maybe you can compute. Then we see that it behaves like this one. And under this scaling, the limit, this one is order 1. Maybe we can neglect this one, but anyway, we can observe what is the limit. Okay, so we have two noises. One is coming from Kawasaki part. The other one is coming from Glauber part. Anyway, we have two noises. Both survive under this scaling. And then we have to study this nonlinear term. So the main task is to study this part. This is coming from the Glauber part. Then the idea is so-called so-called the Boltzmann-Gibbs principle. So the idea, or what we have to prove, is the Boltzmann-Gibbs principle. This is roughly means averaging of the microscopic functions. Average happens due to the long time average and also very wide space average. Then the idea, the Boltzmann maybe, we can replace it by the ensemble average. But the ensemble is not unique. In our case, it's a Bernoulli product measure. Therefore, we have to choose the ensemble. So very carefully. And this principle is the averaging means, in this sense, ergodicity and local ergodicity, and then we can make a Taylor expansion of that. That is called, sometimes called the Boltzmann-Gibbs principle. So we have something, so this is very complex object, but the first step is we replace this one by its average. So this is a microscopic function, depends on the configuration, but we replace this by the average, f. F is the average, ensemble average, this one. But density changes. Density changes this. So we take a density by this one. Then in the next step, we make a Taylor expansion. So then we have this difference. Then we make a Taylor expansion. The first term is f prime, rho minus rho k. Rho k is the solution of the nonlinear PD. Then the second term, maybe f double prime and this square. Then coming back to the psi n, the fluctuation field, we would have this formula. So we have to prove this statement mathematically, but let's assume that this is true. Then we expect we can replace this rather complex term by this one, and then everything is written down by using the fluctuation field. Then what we proved is, in fact, with Claudio Landim and also Sunder Sethuraman, this replacement is true at least if d equal 1 or 2, and also k is smaller than delta times log n to the 1/3. So the condition k is rather bad. But anyway, we have such situation. So then we can replace, sorry, shown up to the linear term, not the quadratic term. So this Boltzmann-Gibbs principle is rigorously shown up to the linear term, the first term, only first term when d equal 1d or 2d, and then the k is smaller than this one. Of course, we want to go to the second order term, but at the moment we don't reach to that level. Okay, then maybe I don't have much time, but roughly we just gather all information from the martingale term. We have this one, and from the Kawasaki part we have this one, and also from the Glauber part we have this one. F prime is the Taylor expansion, the first order term, and maybe if everything goes smoothly, we have maybe the second order term. This is not done. But at least this first order, without this one, it is done with Claudio and Sunder. And then we have A is Laplacian to the stretched direction plus this nonlinear term, which comes from the Glauber part. Then we have a very big factor K here. So we want to study what happens K goes to infinity. So these noises are, so maybe this goes away. But these noises are already order 1. Then what happens K goes to infinity? Then actually the principal eigenvalue of the A is 0. So this is actually positive operator because we have a minus. And this is a non-negative operator on this L2 RDZ. Then the principal eigenvalue is 0, and there is a spectral gap. Actually, it is known. And this 0 is simple, and simple eigenvalue, and the corresponding normalized eigenfunction is given by this one. So this is a profile changing from rho minus to rho plus, which is a solution of the standing wave. Then the derivative is gives the eigenfunction, in fact. Then as k goes to infinity, everything is, in a sense, projected to the normal direction, to this function, because the k becomes very large. And we have a 0. So if next eigenvalue is positive, therefore, other part anyway vanishes because we have a very, very strong factor here. Therefore, everything shrinks down to this one, but only to the normal direction. Therefore, we can prove that this one converges to the tangential direction, we don't know. But the normal direction is projected a very special function like this one. Okay, maybe I don't have time. Time is almost up. Huh? Okay, thank you. So then, actually, okay, so we want to know that everything is projected to this one, to the normal direction, and the tangential direction we still have. So we want to get the information from this equation for the tangential direction. Then what we get is this stochastic PD, but we only have the linear term, and noise term is summarized in this way. So our result up to now is this one. So this is not published yet, but d equal 1 or 2, and k is smaller than this. Then this converges to this, and then this one is governed by this stochastic PD, linear stochastic PD. And the interpolation, so we consider only the fluctuation of the density field, not the interface, However, this implies this is a very special form of the function. Therefore, this implies the fluctuation of the interface, in fact, interpretation of the result. Actually, maybe I should stop soon, I think. So this is defined in this way. Therefore, we come back to this density profile. This is random. Just putting this here, and then you have this one. Then it is projected to this E, the function E. That is a U0 prime Z over this. Then this is small factor. Therefore, this is the Taylor expansion of the U0. So the variable, the U0 becomes this one. So this means the density field behaves like this profile, always profile, but the center of the profile moves but under this scaling, moves at the point x bar. Therefore, in a sense, we have a picture that the keeping the shape of this profile, the interface actually moves according to this one. Therefore, we have a stochastic belief for the interface. Okay, maybe I should stop now. So this is a more precise statement. And also, we have some heuristic argument to derive the sum. We assume the k is a log n to the 1/3. Therefore, we don't reach. But if we can reach to this level, maybe we have some second order term, third order term. This is just conjecture. We are still far away from that. And also KPZ type things, but still we are far away. But anyway, we want to discuss further problem. Okay, thank you very much. I should stop.
Okay, thank you very much for Professor Funaki's wonderful talk. Any question or comment?
My question is about even in Gaussian fluctuation, how we can interpret the exponent k power -3/4.
Log n?
No, it's not on log n.
So
in the
scaling,
normalization of k.
Okay.
Yeah. Why here it is k?
So this one.
Yeah.
This one is introduced to make the noise term order 1 in the limit. Otherwise, maybe you don't get a fluctuation. So we need a
Can we see this order holistically?
We just compute the quadratic variation.
Okay. So it requires a computation.
Yeah. This one. So if it is smaller than, then this goes to 0. If it is bigger than, then maybe it diverges. Therefore, we chose the proper way to get this part to survive in the limit.
Okay, thank you.
Thank you for the question. Any other question or comment?
Maybe a question about the global dynamics. So do we force the number of particles to be conserved? I mean, the global dynamics with Cx, the annihilate and the creation are in the same amplitude.
Okay, so in our case, k is much smaller than n square indeed. So you are saying that when the k is similar. Sorry, not this one. Maybe. Okay, so maybe you are saying the scaling about this.
Yes, I mean, so with the flip rates, so we have created a particle in one side or annihilate a particle in one side. Is that it is the number of particles are always conserved, or it is conserved in a for the large time limit, or it is exactly conserved?
So if k equals 0, the particle number is conserved for all time. However, of course, this Glauber part destroy this structure. However, in our case, k is much smaller than this one. So compared to this conservation law, this changes very slowly in a sense. Therefore, macroscopically, of course, the total number, so the law is not constant. So if you integrate over the torus, it is not constant. However, it changes. This part changes much slowly. Therefore, macroscopically, we see something.
Oh, okay, thanks.
So we have time for a final short question. So if now, let's thank our speaker again.